So the foundational block for the entire deep learning, which is almost synonymous for AI today. If someone says, I work in AI, just, just think that they are talking about deep learning. They are talking about um, um, the neural networks, right? So the for this concept called deep learning, for this concept called neural network, the foundational block of it is called the perceptron. And today, in today's session, we are going to learn about these perceptrons, how these perceptrons work, and how we can connect a lot of perceptrons to mimic what biological neurons does in human brain. But unfortunately, we may not create millions of them. In human brain, we probably have millions or even billions of such neurons. We don't know how many neurons exist. We would not be able to create so many perceptrons, but we would create a handful of perceptrons and how we connect them. So that is why the name neural network. Neurons are connected in the form of a network. And this connection of neurons try to learn for a given objective so that it can perform the tasks in future. It can perform the decision making into the future. So that's why this perceptron is going to be our basic building block of the entire deep learning. Deep learning is still a very heavy subject. We are probably not going to talk about the most complex things of deep learning, but just to begin with, let's see how a simple neural network works in principle, how they replicate the behavior of a biological neuron. Now, if you see this picture, you have inputs which are given in the form of x1, x2, x3, so on. So think of these inputs as the inputs that a biological neuron is receiving through the help of these dendrites. So we are giving these inputs. So x1, x2, x3 are our inputs, which are the input variables. Then we are multiplying these inputs with some weights and aggregating that in the next layer. So this layer, think of this as the cell, the nucleus of the biological neuron. So these inputs are multiplied by certain weights and summed up in this particular layer. After getting this sum, on top of this value, we are going to apply something called as an activation function. And after the activation function, we get an output. The processing is very simple. On this side, we are giving inputs x1, x2, x3, so on. Each input is multiplied by a weight and summed up in the next layer. On top of this, we are going to apply an activation function, and depending upon what activation function we use, it would generate an output and we receive an output. So this is exactly what a perceptron does, but not as simple as that, right? We need to understand every piece of it, like what happens here, what type of activation functions are there, how it generates an output. Okay, now let me explain that with the help of a simple example. Let's take a whiteboard, and let's see that with the help of an example. So these are our inputs. Let's say I have 4 inputs, and this is my neuron block. Okay, this is my neuron block, and each input is connected to the neuron. So each input is connected to the neuron, and these connections are given weights. Let's say this is W1, this is W2, this is W3, and this is W4. We call them as weights. And this is your X1, this is your X2, this is X3, this is X4. These are the 4 inputs that is feeding this nucleus. You call this as nucleus, or you call it whatever it is. That's what is happening here. And this layer is the summation layer. So what is the summation layer for this? So this is W1x1 plus W2x2 plus W3x3 plus W4x4. This is what is happening inside this summation layer. The output, let's say the input is all these values. Let's call this output as O. And this output is given to an activation function. So we represent this activation function as phi. So the output generated by the summation layer is O. So on top of this, we are applying an activation function, and this activation function will generate your output Y. So that's the functionality of a neuron, or we call this as perceptron. Now let's deep dive into this activation function, because summation function is very easy, straightforward. Each input multiplied by certain weights and summed up together is the summation function. So summation function is pretty straightforward. But this one here, activation function, is the tricky one. Now let's see what this activation function is. There are many types of activation functions. For example, we have something called as a step function. We have something called as the sigmoid function. Then we have tan hyperbolic, tan H. Then we have ReLU. Then we have softmax, and there are more activation functions being researched, right? But for now, let's stick to these functions, right? Now, step function. So what is a step function? If you are familiar with the digital signal processing, you might be already aware of what a step function means. So as long as the output of this is negative, it would be 0. Once it is above 0, then it would be giving an output like this. So this is your step function. As long as the input is negative, it will not give any output. It would give the output as 0. The moment it hits something, then as long as the input is 0 or positive, it would give a unit step as the output. So this is how a step function, a step activation function will work. For example, if the summation of these weights is, let's say, -1. So this is -1. when input is -1 to the activation function, what is the output? Output is going to be 0. When input is 0, then the output becomes 1. When the input is anything above 0, then the output is always going to be 1. So that's the step activation function. And similarly, we have something called as the sigmoid activation function. One of the most popularly used activation function is sigmoid. Now, let's see what a sigmoid activation function would look like. For low values of input, it would stay closer to 0. And at some point in time, it would try to jump. It would look like a S curve. Okay. And this is exactly at 0.5. So this is called as the sigmoid curve, right? So this can be written as in the form of an equation. Output y is equal to 1 by 1 plus e to the power of minus x. So depending upon your input, whatever be the input, the output is y is equal to 1 by 1 plus e to the power of minus x. So this function is called as the sigmoid function. And a sigmoid function will always gives you output between 0 and 1. So it would always give you an output between 0 and 1. And because it gives you an output between 0 and 1, this can also be treated like a probability. And that's why sigmoid function is a very popular function and very commonly used activation function. Then the next one is the most heavily used one is ReLU, which stands for Rectified Linear Unit and simply called as ReLU, popularly known as ReLU. Let's see what ReLU is. When x is negative, ReLU would always give the output as 0, and when it crosses 0, when x crosses 0, it would linearly increase. So that's why it is called as rectified linear unit. The next one is tan H, tan hyperbolic. So it would also look like a sigmoid activation function, but it is going to be between -1 to +1. Sigmoid gives between 0 and 1, and tan H will give you between 0 and -1. So this is how a tan H function would look like. So in mathematical form, this can be represented as e to the power of x minus e to the power of minus x divided by e to the power of x plus e to the power of minus x. In fact, we have learned about all these equations in calculus, but we never paid attention to it, or maybe we did not realize the potential of them in practical usage. And the moment you hit artificial intelligence, machine learning, and deep learning, all those functions, every mathematics that we have learned through our school college days comes and hit us back hardly that, okay, this is where probably all these things are being used. And then we have this softmax. Softmax is generally used in the output layer. Let's hold on to that for a moment. I will explain what output layer is in a while. So softmax is used whenever we have a output which takes more than 2 values. So it can be written as y hat is equal to e to the power of xi divided by sigma of e to the power of xi. For example, if we have three outputs generated, that is 2, 6, 9, then your three outputs of the softmax is e to the power of 2 divided by e to the power of 2 plus e to the power of 6 plus e to the power of 9. And for the next one, e to the power of 6 divided by e to the power of 2 plus e to the power of 6 plus e to the power of 9. And last one is e to the power of 9 divided by e to the power of 2 plus e to the power of 6 plus e to the power of 9. Softmax is used for multi-class classification. Yesterday, we have seen an example for binary classification, right? But when do we use softmax? We use softmax for multi-class classification. So these are the popularly known activation functions. Okay, let me take a pause here to see if there are any questions around this. Feel free to post the questions because this is the interesting piece of the entire neuron, perceptron. If you understand this, then we can easily understand the other aspects of it. Okay, let's see here. Let me give the inputs like 1, 0, 1, 0. So I'm giving 4 inputs, 1, 0, 1, 0. These are my 4 inputs. And let me give the weights as 0.5, 0.2, 0.1, minus 0.1. We can give both negative and positive weights, right? So let's randomly give some weights. And this one, inputs are 0, so we can ignore them. So this is 1 into 0.5, which is like 0.5. This one is 1 into 0.2, which is going to be 0.2. So 0.7 plus 0.2 is, 0.5 plus 0.2 is 0.7. That is what is generated by the summation function. So let's write that. We are passing values like 1, 0, 1, 0. So this is my x1, this is my x2, this is my x3, this is my x4. And the weights that we are giving is 0.5 and this is 0.3, this is 0.2, and this is minus 0.5. And what would be the summation? 1 into 0.5. So that is the first one. 0 into 0.3, no need to write. 1 into 0.2, so that is this one. And 0 into minus 0.5, no need to write this. So the summation is giving you an output of 0.7. So that's the output here. The output here is 0.7. Now, let's say we are using a sigmoid activation function here, right? So this is pi of 0.7, right? So the output of this is 0.7. So this is pi of 0.7. So that's going to be passed to the sigmoid. So what is the sigmoid equation? 1 by 1 plus e to the power of minus 0.7. So this will give you some value. So that's the output generated by your neuron for the given inputs and for this given weights. Okay, let's say this is minus 0.7, right? So let's say this is a small value like 0.3. I'm just roughly quoting that. So this is the output generated. Okay. So this step, whatever that we have done so far, is called as the forward propagation. What happens in forward propagation? In forward propagation, we will take the inputs, and from the input, we will generate the output. So the output that we have generated is 0.3. So this is our Y. Next, is the output generated by our model good enough? Maybe or may not be. In this case, the original output, so this is the Y hat that we have generated. The original output is supposed to be Y is equal to 1. But the output that we have generated is 0.3. That means output that we have generated is not close to the actual value of Y. What we have to do here? We have to make adjustments to our neuron or perceptron so that the output that we have generated here is very close to the actual value. If not same, at least it should be close to the actual value, right? So how can we make this output close to your actual value? By changing these weights. So if we can change these weights, of course, the output of the summation equation will change, and the output of the activation function will also change. Maybe we will see something closer to Y is equal to 1. Okay, now let's do this. Now let's see, this is the output of our first iteration. Now our error E is equal to original 1 minus 0.3. So our error is 0.7. Our error is high and we want to reduce this. This is exactly what we did in machine learning. So how can we reduce this error? Okay. So we can reduce this error by changing the value of your W's. So this is your W1, this is your W2, this is your W3, and this is your W4. Now, if we change the value of W1, the output will change. But the question is, how much we should change the W1 from the first iteration. For the first iteration, let's write the values of the first iteration. W1 is equal to 0.5. So W2 is equal to 0.3. W3 is equal to 0.2. And W4 is equal to minus 0.5. So this is what our first iteration is. Now for the second iteration, so let's call this as W11, W31, W21, and W41. So that we know that these are the values of the weights during our first iteration. Now we need to change the values of the W's. Then the question is how much we want to change these values. Let's do that. So Wi, I am representing this as the weight of ith input. Wi for iteration k plus 1. So this is the suffix is the the weight of the inputs, and this is the iteration. So Wi k plus 1 is equal to Wi of the kth iteration, the previous iteration, minus the eta times the gradient. So what is the gradient? dy or dou y divided by dou wi. Or I could call this as dou e, because we are trying to reduce the error, right? So dou e divided by dou wi, the partial derivative of the weight, respective weight. So that's why I explained the concept of gradient descent yesterday. So if you do not know what this gradient descent means, now you would not realize why we are doing this step. So whenever we want to update the weights of the k plus 1 iteration, we either subtract or add something from the previous iteration. So how much we subtract or how much we add is decided by the learning rate eta. So what is eta here? Eta is called as the learning rate, and this one here is the gradient. Generally, we represent the gradient as delta E. So I can write this equation as Wi for the k plus 1 iteration is equal to Wi of the kth iteration minus eta times the gradient of the error with respect to Wi. Okay, so far so good. But we want to find out the gradient value. The gradient value is dou E by dou Wi. So the gradient of error with respect to the weight I. So for example, W1, if I want to update W1 for k plus 1, then I need to know what is the W1 value for the kth iteration minus eta times the gradient of the error with respect to W1. So this is the equation. The problem here is our error is here. The error is y minus the y hat. But W1 is not directly connected with our error. In between, we have a summation function, and in between, we have another function. So we cannot directly find out what would be the gradient with respect to W1. What would be the gradient of error with respect to W1, right? So what I would call this as OR, the output on the right hand side, and this as OL, the output of the summation. Then we are going to find out the gradient. So that is dou E divided by dou W1 using the chain rule of calculus. It is proved by Euler's theorem. So if you remember the chain rule, what is chain rule? So if I want to find out the derivative or partial derivative of a function which looks like this, g of h of f of x with respect to x. So fx is not directly a function of this. So in between there are a lot of different functions. So how can we do this? Then we can find this derivative using the chain multiplication rule like this: dou g divided by dou h into dou h divided by dou f into dou f divided by dou x. So this is called as the multiplicative chain rule in calculus. So I want to find out dou of this entire function with respect to x. But this entire function is a combination of multiple functions. So I would not directly derive this to find out the derivative with respect to x. So we are splitting this dou g by dou h by dou f into dou f by dou x. Now, applying the same principle here, my error is directly connected with OR. So I am going to find out dou E with respect to dou OR. And my OR is directly connected with OL. So it would be dou OL with respect, dou OR with respect to dou OL. Then my output of this OL is directly connected with W1. So this would be like dou OL with respect to dou W1, right? So to find out this derivative, we need to find out all these derivatives and multiply them together so that we would get this derivative. Once we get this derivative, then we go ahead and apply this W1 k plus 1. Let's say our W1. What was the value of W1 in the first iteration? 0.5. So this is 0.5. And the learning rate, I am taking my learning rate eta. Eta is equal to 0.1. That's my learning rate. And learning rate is a parameter. We have to choose the value of it. So this is called as hyperparameter. As a developer, we decide what should be the value of your hyperparameter. Okay, 0.5 minus 0.1 times, let's say the gradient is 2. I'm just giving you a brief value because calculating all of this with the help of partial derivatives now would be slightly difficult. So that is why I'm just going with some value. I am assuming that my derivative is 2. So the next iteration value of W1 is going to be 0.5 minus 0.2, which is going to be 0.3. So we found out the value of W1. So similarly, we have to find out the value for W2. So the same thing will apply. Dou E by dou W2. We need to find out this derivative. So this is dou E by dou OR because E is directly connected with R. Dou OR divided by dou OL, which is connected directly. Then dou OL divided by dou W2. Now, if you just cancel all of this, now you get this output, which is dou E divided by the derivative of error with respect to W2. Let's say this is 0.1. Now, W2 k plus 1 is equal to, what was the W value for the W2 value for the first iteration, which is 0.3. So 0.3 minus 0.1. Learning rate is fixed. Minus 0.1 times 0.1, which is going to be 0.01 minus 0.01. So this is going to be 0.29. So like this, we will update the weight of W3 for the k plus 1 iteration. We will update the weight W4 for the k plus 1 iteration. Then again, do the forward propagation. So this one, like taking back the error to update the weights, is called as backprop or backward propagation. Once we update the weights, we will again compute it forward. Say for example, now W3 value, once we have changed this is let's say 0.3, and W4 value is what was the value of W3 before? Let me see that. W3 is 0.2. So let me change this to 0.5 and 0.4 and W4 to minus 0.2. Okay. Now again, let's do the forward propagation. What are the new values of our W1, 2 second iteration? W12 is 0.3. W2 2 is going to be 0.29, and then W3 second iteration is going to be 0.4 and W4 second iteration is going to be minus 0.2. Let me write it here clearly. W1 second iteration is 0.3. W2 second iteration is 0.29 and W3 second iteration is equal to 0.4 and W4 second iteration is equal to minus 0.2. So these are the new values. Now let's do the forward propagation. 1 into 0.3, because our inputs are x1 is equal to 1, x2 is equal to 0, x3 is equal to 1, x4 is equal to 0. So 1 into 0.3 plus 0 into 0.29 plus 1 into 0.4 plus 0 into 0.2. Okay, so 1 into 0.3 will remain 0.3 plus 0 plus 0.4 plus 0. So what we got now as an output in the forward propagation, y value at second iteration is 0.7. Look at the previous value. Our previous value, when we randomly initialized the weights, the output that we have got is 0.3 and the error is 0.7. Then we learned back on how to update the weights in a way so that our error will decrease. Why we are finding this gradient? The gradient is to tell us in what direction, if we move, we will decrease this error. So that is exactly the minimization concept of calculus. So we want to minimize the error. So if we want to minimize the error, in what direction we have to move this W1, W2, W3, W4. So to find out in what direction we have to move, we are finding all these gradients, the partial derivatives. And we updated the weights in the second iteration. And in the second iteration, we got an output of 0.7. So that means we got much closer to our expected output. Our expected output is 1. Now we have moved slightly closer to our expected output, right? So this is iteration 2. And if there is a possibility to improve further, yes, we will try to improve that further. Let's say in the next iteration, we will find out W13, W23, W33, and W43. Let's say W13 is increased to 0.4, W23 is increased to decreased to 0.26, W33 is increased to 0.48, and W34 is increased to minus 0.3. Now, our forward propagation again, this came from the backward propagation. So the updation of the weights happened through the backward propagation. So now let's talk about the forward propagation again. 1 into 0.4 plus 0 into 0.26 plus 0.48 into 1 plus 0 into minus 0.3. So these things not required. 0.4 plus 0.48. Now the output that we have generated is 0.88. slowly we are crawling towards the expected value of the output, right? So this is exactly what happens inside the perceptron. Why people feel it so difficult is the moment they see all these things like, okay, there is a activation function, there is a feed forward layer, or we call it as forward propagation, where we generate the output from the inputs. Then there is a backward propagation layer where it is also called as the feedback layer, where we will try to find out the gradients of error with respect to the weights in order to know which direction to move if we have to reduce that error, if we have to get our output closer to the expected value. So this, in a nutshell, is simply called as the neuron. Artificial neuron, or the other name that we use is perceptron. Okay, fine. Let me pause here and see if there are any questions around this. I hope you are able to follow this so far. If you have understand this particular example of how a perceptron works to generate an output that is very close to the input that you have given, then half of the complexity is already done, and you do not have to worry about it. When you do the programming, you have a lot of built-in modules. You do not do any of these derivatives like in hand. Yesterday, that's why I show you that machine learning example. We spoke a lot about how a decision tree is learning using the measures of the measures of impurity like entropy, Gini, information gain, repetitions, etc. But when we actually did that program, we did not calculate any of those things by hand. The algorithm is built in such a way that it will slowly try to learn and get the best tree as your output so that you can use that tree in your future decision making. Even in the case of a neuron also, you would not see any of these things, any of these calculations. We will give these inputs and we will create we will decide what activation function that we are going to use, and we will give the output, desired output. I want this output from this inputs. Okay. Summation function is same throughout. So we would not have any changes to the summation function. Only change that we perform, only thing that we decide here is the activation function. In this example, I used the activation function, let's say a sigmoid activation function. In some other case, we might use a ReLU activation function. In another case, I might use a softmax activation function, right? So depending upon what function you use, these derivatives, the concept of derivatives will change, the derivation will change. But you don't do that manually. It is taken care by the programming languages. Only thing that you decide here is what is the activation function that we are going to do and what is going to be our learning rate. And learning rate is very important. Okay. I will explain you the importance of a learning rate. Why we give this learning rate. What happens if we don't use this learning rate? So I want to find out the optimized value between these two parameters, right? The beta 1 and then the beta naught. That's what the example that we used yesterday. This is beta naught and this is beta 1. So this axis, the third axis, is the error axis. So we want to find out the minimum value of the error. So this is the minimum value, E minimum, that we have to find out. When we randomly initialize the values of beta naught and beta 1, let's say this is the value of error that we have got. So this is at iteration 1. So I am call it as I is equal to 1. If we don't use this learning rate, what can happen through this process is then we change these beta naught and beta 1 values drastically. That means we change them by a very large magnitude. When we change them by a very large magnitude, what happens? At I is equal to 2, at the second iteration, we hit here, I is equal to 2. And then in the next step, we might go and hit here. So this is equal to I is equal to 3. So we would be like toggling back here and there, here and there, here and there. And sometimes it might even go haywire. That means the error might start to increase as well. And we would never reach this minimum point. The moment the error increase here, we might think this is our minimum point and we would stop here. That should not happen. So this problem happens when we decrease or increase the weights with a large magnitude. Instead, what we are going to do is we are going to decrease these weights by a very small magnitude. So that means we are going to go down the hill step by step. So that's why it is called as the gradient descent. So I is equal to 1, then I is equal to, so we would do this. So this is I is equal to 1. And when we change these values of beta naught and beta 1 by a small magnitude, how can we change this by a small magnitude? By choosing the eta value as a very small value. Now what happens? We will take gradual steps, equal size steps, slowly until we reach this point. And when we see an increase, we would stop and say, hey, I have hit my minimum value, so I would stop here. So to control the steps, like how we are going to move, we are using this learning rate. And this optimization here is called as the gradient descent optimization. So using this gradient descent optimization, we are taking very small steps of gradients. By choosing a learning rate of small value, I am controlling that. I am taking very small steps down the hill so that I reach this minimum global point. Once I reach this minimal global point, I would try to stop my iterations, because any further step forward is going to increase my error. And that's how we would reach this minimal global point. If we don't do this gradient optimization, like if we don't update the weights like Wik plus 1 iteration is equal to Wik minus the gradient directly, that is dou E by dou W1, we might make this error of toggling the space, but we would never probably reach this global minimum value. So that's why this is not allowed. We won't directly use the gradient. To make these smaller steps towards this minimal point, we would always try to iterate with very small steps, and the step size is controlled by our learning rate. So eta is our learning rate, dou E by dou W1. Now this eta is also decided by us. So in this neural net, in this neuron, I would name this, I would call this as perceptron. In this perceptron, what we did is we randomly initialized the weights, that is on us, and we choose a activation function that is also on us, and we choose a learning rate. A learning rate that is good, so that the learning process is stable and slow. If we choose a very high value of learning rate, learning process won't be stable. It would be toggling here and there, and we might end up with a non-local value. If we choose a very small learning rate, like sometimes we can choose a learning rate which is like as small as 0.001. This is like too small. It's okay, but what happens is to reach this point, you might take 1,000 iterations, and you need to do this gradients over 1,000 iterations and update the weights over 1,000 iterations to reach this minimum point. You would reach, but the only thing is computationally it becomes so intensive because of too slow, and it takes too many iterations to reach that. Okay. All this process is done by your machine. You don't do any of these things. Believe me, if really we have to do all these things, there won't be any person who would be practicing AI or who would be learning AI in the world, because these are not fun stuff. These are very, very complex stuff. And that's the reason we have inbuilt modules in Python, inbuilt modules in other programming languages, which does all these steps behind the scenes. Imagine taking a learning rate of 0.01 and iterating over 200 iterations. So 200 forward propagations, 200 backward propagations, 200 updation of weights, and every time you do a backward propagation, you need to calculate 3 gradients because it's not directly related. So you need to use the chain rule to derive them. That's enormous amount of calculations just to train one single perceptron for one observation. And here it is only one observation, right? In practicality, you would be giving a lot of observations, but for simplicity, I'm just using one observation. And so many calculations to generate a desired output from one input with only one single perceptron. That's why neural networks are computationally so intensive. CPUs, when we go to complex training, complex models training, like trying to find out patterns in images, trying to build a image classifier, you might try to train with thousands of images at the same time. With a complex network, it might be clogging your CPU resources to 100%. And CPUs may not be scalable beyond a certain point. And that's why in deep learning, we use GPUs rather than CPUs. GPUs are many times faster in doing these type of computations than your CPUs. Okay, let's keep that aside. Any questions so far? Great. Now you understand why, though neural networks was there conceptually in research papers for a very, very long time, it was not really used in practical applications. The only reason for that is the limitation of the infrastructure. The infrastructure would not be able to cope up with these many complex computations, and the memory issues are very common. I'll show you example tomorrow where we would build a simple neural network example, and you can imagine the amount of data that is getting stored in the RAM when we execute such type of computations. The data size in the RAM goes into a few GBs. Though the input data is there, just the weight matrices will go into GBs. And another infrastructure blockade that we had been facing for quite some time is not having enough RAM to train them. Nowadays, even laptops have 32 GB RAM, so that's not a big deal. But olden days, having 4 GB RAM, 2 GB RAM was a big thing. So you would never be able to train these type of neural networks on top of it. So this is a perceptron. So what we have covered so far is just one single perceptron. But a single perceptron is not good. A single perceptron is just as good as, for example, if we consider that linear regression example yesterday, a single perceptron is like trying to find out this line. The reason why we are speaking about neural networks is because there is the relationship between your input and output is not linear, and a linear equation like y is equal to mx plus c is not going to fit. So it is much more complex. So if we talk about a time series, you would have a time series, a stock price which is looking like this. So you would never be able to try and explain this variation of a time series with a linear equation like this. So we need much more complex models. So how do we bring that complexity? So to bring that complexity, we are going to introduce something called as MLP, which is called as multi-layer perceptrons. We will never use a single perceptron. A single perceptron would never be able to make any good decision making for us. So we are going to have a network of neurons, and that network of neurons is called as the multi-layer perceptron. Okay, so how does a multi-layer perceptron looks like? How does a neural network is going to look like? Let's see that. So our inputs are going to be like this. Let's say we have inputs x1, x2, x3, x4, x5, and x6. So the inputs are connected to the next level layer, which we have neurons. Let's say I have created 6 neurons in the next layer. Why I created 6 neurons in the next layer? Because I have 6 inputs, and it doesn't have to be 6 all the time. Okay, remember that point also. Now, each input is connected to each neuron. So every input is connected to every neuron. So this one is connected to this neuron. This input is connected to this neuron. This input is connected to this neuron. This is connected to this neuron. Okay, it's becoming way clumsy. So let me draw something slightly simpler, because yes, we can build a multi-layer perceptron for regression as well. Yeah, just that the activation function we have to use will be ReLU. And I will, that's what I'm going to talk about in the next 2 days, right? We have to make a lot of decisions, and the decisions that we make is going to decide how good this model is, how good the output of your model is. If all of these things is done by Python itself, why do we need a AI practitioner or an AI engineer to do that? Anybody can do that, right? No, still, as a AI practitioner, we have to make a lot of decisions to get the best output from a given model. And let's see what it is going to be. So I'm going to have only 4 inputs, x1, x2, x3, x4, and my neurons are also going to be 4. So these are the 4 neurons. So we would be connecting each neuron with each of these inputs, and like this, like this, like this, and then like this. Same for this, Same for this, this, and then this. So this is the hidden layer. I am representing this hidden layer as H1. Let's say I have one more hidden layer like this. I am representing this H2. These are neurons. So I have four neurons here, N1, N2, N3, N4 in the first hidden layer. And this hidden layer is connected through another hidden layer like this. And finally, an output layer where we have, let's say, two outputs. Depending upon our objective, we may have two outputs. If it is regression, we will have only one output. This is a binary classification, so that's why we are creating two outputs. If it is a multi-class classification, we may have many outputs also. So how we try to put that network architecture, we have to understand that. Okay, so this and this and this and this. Okay, so this is the output layer. So this one here is called the network of neurons, or we simply call this as the neural network. So the inputs are four. There are two hidden layers. In hidden layer one, I have four neurons. In this hidden layer two, I have three neurons. The total number of weights here is 4 by 4. So that is like 16 weights. And the total number of weights here is 4 by 3. So that's like 12 weights. And here it is going to be 3 by 2, which is going to be 6 weights. And that's how you get this. What is this 4 by 4? Let's say this is W11, this is W12, so on. Okay. Why do we need such a complex layer? Why do we need to have so many hidden layers and so many neurons in the hidden layers? That's exactly the reason why we came for neural networks. What is happening here is, so this is our input, this is our output. We are trying to divide your input and output into multiple smaller zones. So through this multiple complex layers of connections, where the relationship between input and output can be like this, and you are trying to learn such non-linear relationship. Now, for this one here, for this time series here, which I have represented, this below line is a better representation than a line which just looks like this linear line, right? So to bring this non-linearity, we are trying to build such a complex network. What are the decisions that we have to make as a data scientist? So these are all the decisions that we have to make as a AI practitioner, as a data scientist, as a ML engineer. You call any name, but if you have to build these type of things, first thing is, what is our network architecture? So in the network architecture, we have to decide how many hidden layers are there and how many neurons in each hidden layer. That we would see in the tomorrow exercise. Okay. So these are called as hyperparameters. Nobody would be able to directly say, hey, in this case, two hidden layers will work and four neurons in each hidden layer will work. Even the best of the best practitioners would not know this. We have to do a lot of trial and error. First, I will start with one hidden layer with 4 neurons in it because I have 4 input variables. So at least I would go with 4 neurons here. If this is not really giving me a great output, then I would increase one more hidden layer. And in the second hidden layer, maybe I'll try to reduce the neuron so that it doesn't become too complex. And I will try to generate the output and see how good this model is. Even after this, it is not really doing a great job. I would try to increase a hidden layer, or I will try to increase the neurons in the hidden layer. So everything here is an iterative process, and we learn through this iterative process. And finally, we have to decide the other parameters, like what should be the learning rate. So this is the learning rate. And in each of these neurons, so think of these neurons as summation, because each neuron should have a summation function and an activation function. So each neuron will have a summation function and activation function. So what is the activation function here? What is the activation function here? Generally, the hidden layers, we use the activation functions as ReLU. So this is going to be ReLU. So in the hidden layers, I would prefer to go with ReLU. And in the output layers, so these activation functions in the output layers is typically decided by the objective. When we have binary classification, we might use sigmoid. When we have multi-class classification, we would use softmax. When we have regression problem, then we would simply use a ReLU again here. So the output layer activation functions are decided by the objectives. So these are all called as the hyperparameters. What values of hyperparameters work well in getting the desired output from your input? We don't know. That is what we are trying to learn. So we try to train this model with repeated execution by changing these parameters until we get a satisfied desired output. So this process is what we call as the training process. So we have to repeatedly change the network architecture, activation functions that we are using, the learning rate, the number of iterations, etc., until we get the desired output. And this network here is called as the fully connected network, or the fully connected layer. In a fully connected layer, every input is connected to every neuron in the next layer, and every neuron in the hidden layer is connected to every neuron in its next layer. So that is why the name fully connected layer. For stock market, to get predictions, is it possible to use classification algorithm? No. For stock market is a typical problem. We call this as a time series problem. And we would be building a time series analysis or forecasting. It is also called as forecasting. It is not a regression problem also. It is a forecasting problem. Right. Now, how do we train all of these things? I'll just take 5 minutes and I'll be opening up for questions. Even if it takes a lot of time, I would stay back to answer those questions. So don't worry about this. So these are also complex things, and it is difficult for anybody to program everything of these architectures from the scratch. So nobody would be able to do it. Even if we do it, it might take 1 month to write these type of programs, right? So to help us in this aspect, we have frameworks so that it makes our job easier. It's not just about Python. Even with Python, we would not be able to do this. So this is where the frameworks that are going to help us. The popularly known frameworks You might have heard some of these names already: TensorFlow, PyTorch, Keras, Caffeine. So these are some of the popular frameworks which actually helps us to do all of these programming. In fact, the example that I'm going to show you tomorrow, we are going to take the help of a framework called as Keras to do that, to build that artificial neural network. Okay, so if we have to start the journey of a AI programmer or a AI practitioner, then we definitely need to learn one of these, either TensorFlow or PyTorch or Keras, etc. But one of these is must. It's not just Python. Python is going to be our programming language. So on top of Python, we are going to do we are going to use this framework called as Keras. Programming is going to be done in Python, but the framework that is going to help us is Keras. So I will briefly explain what Keras is and how Keras work and how we are going to use Keras in the example tomorrow. Not just only here, depending upon the objective of what type of application that we are going to build, then we have different architectures. So the popular architectures in deep learning are like this: CNN, which stands for convolution neural networks. So this architecture is very popular in computer vision, especially if you have to learn anything from images, videos, then you would have to use this particular architecture. So what I have shown here is a simple example of ANN. So tomorrow we are going to program a simple example of ANN, an artificial neural network. But these ANNs are not really good enough when we have to learn something from images and videos. So that is when this popular architecture called as CNN comes into the picture. If we are performing something on text data, language modeling, something we are building to do language translations or chatbots, etc., then we use another architecture, another popular architecture called as RNN, which is called as the recurrent neural networks. So RNNs are mostly used for for the applications where the historical data is very, very important. So someone asked about stock market predictions. If we have to do stock market predictions using deep learning, then we have to go with RNN. So RNNs are popular in NLP, the natural language processing, in text, in language modeling. For all of this, we use this. Another version of architecture of RNN, which is called as LSTM, long short-term memory. These are very popular in language modeling, etc. Right? So these are some high-level terms, but I am giving these terms so that in future, if you are preparing yourself to become an AI practitioner, this is going to be your journey. Remember this. First and foremost, you have to understand the process of machine learning. Though we did this with a simple example on day 2, that's not good enough. You need to learn a little more about machine learning. How different algorithms work in machine learning, what are the advantages of machine learning algorithms, disadvantages of the machine learning algorithms. That overview is good enough. Next, to build something in AI, the first step is understanding how neural networks work. what a neuron is, what a perceptron is, and how does the perceptron going to work in reality. Once you have a very good understanding of how neural networks work, then we would start programming them using Python as the programming language and using one of these frameworks. It can be TensorFlow, it can be PyTorch, it can be Keras or Caffeine or whatever it is. Right now, to begin with, one is good enough. I would suggest you have, if you are planning to learn, Keras is the best one to start with. And that's the reason tomorrow I am going to show you an example of ANN using Keras. That's not the end of it. Whenever we want to build complex applications, applications that are capable of dealing with the real world problems, so that's when you have to learn about these complex architectures like CNN, convolution neural networks, RNN, the recurrent neural networks, and GAN, generative adversarial networks, right? A lot of them. This is a never ending game because this is an evolving field. New things keep coming, and we have to keep pace with the industry. So we would keep learning. But for now, if someone says AI, remember that they are going to use either CNN or they are using RNN, which is a popular version of RNN called LSTM, to build applications that involves images, videos, etc. Then that falls into the module called as computer vision. If they are dealing with a lot of text, language, speech, time series, then it falls into RNN or LSTM. This is going to be our final goal as a AI developer. So using this, we should be able to develop applications. But to reach there, yes, the fundamentals has to be very, very strong. So tomorrow I'll show you the ANN example using Keras, and day after tomorrow, maybe I'll show you a brief explanation of what CNN is and how we can build a simple application. May not be an application, complete application, but a image classifier using CNN. So that's going to be the agenda for the next 2 days. So if, okay, there was a question asking which built-in model or command is used for getting gradient descent in Python. In SciPy, in a module called SciPy, you have this gradient descent function built in. If you want to use gradient descent built in, you can go there. But that's where Keras is going to help you. You do not have to explicitly say, hey, this is going to be the gradient descent. You can directly say, hey, this is going to be my neural network, and try to learn how to generate the output from the inputs that I am giving using this neural network. So that would reduce a lot of complexity for you. We can write a custom function also if you want. I'll show you how to do it maybe tomorrow. Please feel free to post your questions. I know this is heavy stuff. Don't get bothered by all those math that is involved there. That's just for illustrative purpose. It happens behind the scenes, so never ever worry about those, that the complexity of the math there. Performance is not same. It depends upon how we are going to train our models. Generally, when we use Keras is a wrapper actually built on top of TensorFlow. So behind the scenes, Keras also uses TensorFlow. So comparatively, Keras would be slightly slower than your TensorFlow. TensorFlow is the one given by Google. They have been using it for quite some time, but they outsourced it in the year 2014-15. And since then, TensorFlow is our go-to framework whenever we want to build AI applications. It's faster, and as well as it can utilize an infrastructure called as TPUs. If you have not heard about TPUs, don't worry about it. Like CPU, like GPU, you have TPUs. CPU, the central processing unit, which is the cores i7, i5, i3, Xenon. This is the processors, right? Next is your GPUs, the graphical processing units. You have GTX series, you have RTX series. Even faster, whenever we have to do AI development, even GPUs can be slower. So if we have to do even faster processes, Google has introduced these processors called as tensor processing units. These are not yet available in any of the commercial laptops or desktops. You need to buy cloud infrastructure for that. Then you would be solely relying on TensorFlow. PyTorch is given by Facebook. It simplified a lot of things for us. There are a lot of fans for PyTorch, though I haven't used PyTorch much in my career. But people who use PyTorch, they say, hey, it's much more easier than Keras. But because I haven't used it, so I would not be the right person to comment about it. So whenever you are trying to do train images, you might be either using the CNN or you might be using GAN. In the hidden layers, I would probably go with ReLU. ANN stands for Artificial Neural Network. So when we combine a lot of neurons, it's called as ANN. And in ANN, these are fully connected. And that's why they are simply referred to as artificial neural network. But in CNN, the neurons are not connected like this. I will explain the CNN architecture on the last day when I show you an example. In CNN, the architecture is going to be very different. So they are not fully connected, and the way they process the data is also going to be slightly different. I'm not sure what you mean by brain signal analysis. Um, Maybe I'm not aware of this topic at all. I'll try to find out what brain signal analysis is and how it is related to AI. Though we work in AI, the application of AI from one industry to another industry could be very different. So I might not be aware of some of the applications or typical applications that's coming from other industries. Okay. Advantages of ReLU activation function over Sigmoid or over softmax. Both softmax, sigmoid, and tan hyperbolic suffer something called as exploding gradient and vanishing gradient. So that's a very tough topic. Okay, I might not be able to explain in 5 minutes. As in when you try to go little more deeper into the neural networks, you would hear these two terms. One is called as exploding gradient and the another one is called as the vanishing gradient. And because they suffer with these two and ReLU doesn't suffer with any of these two, ReLU is the most preferred activation function for many of us, especially in the hidden layers. In the last layer, we do not have a choice because your output has to be in line with expected. So that's where we use the activation functions like sigmoid and softmax, but we don't use them in the hidden layers. Yeah, we can initialize specific weights for the neuron. If we want to. If we leave that to the random process, that is also good. But if we really want to, then we can initiate the weights. Uh, uh, I think Django is a web framework for Python. So if we want to integrate applications after building AI based models, maybe then Django might be useful. But as such, for development of AI, you would not use Django. That's what I said, right? I did not hear this term brain signal analysis at all. I'm not, I don't know how AI is related to this brain signal analysis. So today I will try to find it out and find out the relationship between the brain signal analysis and AI. Then I would be able to suggest you what frameworks are good, what architectures are good for brain signal analysis. Without knowing the concept itself, I would not be able to speak about it. Yeah, there are rules for deciding the number of hidden layers. It depends upon the architecture that we are using, but in general, at the first hidden layer, we would try to match that with your inputs. So if you have 4 inputs, at least we would try to match with your 4 neurons in the first hidden layer. And going forward, we will try to reduce them to an extent of half. For example, in the first hidden layer, if I have 4, I might want to reduce them to 2. That's the max that we would reduce. But general principle is we would keep them at least more than half in the next layers. So that's how we try to proceed to your end output layers. All of them are open source. That's the beauty of AI, machine learning. Anything that you talk about in machine learning, in AI, everything is open source. That's how the world has actually progressed. Gone are those days where people build these proprietary tools and keep it for themselves. There might be still few of them. Google, when they were using TensorFlow, they did not give this as a tool for anybody outside. They were just using it, but they thought that, okay, the rest of the world also has to catch up with them, then it would be good. So they just open sourced it. Okay, this is the TensorFlow framework. You are free to use it. You don't need to buy any licenses from us. And that's when, since 2014, 2015, this field of AI kick-started. Before that, very hardly you see, like, you might probably hear like 1 in 1,000 people might even know a little bit of AI, but today everybody talks about it. That's just because of this open source, rapid growth because of the open source.